In this video, we're going to discuss some of the intermolecular forces and properties of solids, or at least how we go about analyzing some of them. Here we see a few atoms arranged with each other. So each of these is a single layer of atoms. And so color-coded to show the layers here, but they're separated at the moment. When a second layer of material starts to add to the first, as we're growing a solid, it has options. It could stack directly on top. And so you could make vertical columns. This would be, say, stacking a bunch of Coke cans on top of each other. And so every layer is exactly lined up with the layer below it. You could also offset them. You could keep the lines the same, but you could have the top layer be half an atom off, and so that you have a little bit of a zigzag. Think about bricks. If you ever see a brick wall, you tend to have your bricks not perfectly in a line vertically, but half and half back and forth. Well, you also could shift them down as well as over and end up kind of being in between. In this case, you're centered over the holes that were in the layer below. So all of these patterns are possible. You could have directly above, you could have inline but offset, or you could have two-direction offset. When you then have your third layer, well, if this one lines up with the original, then you have an AB pattern. You just go back and forth between the two. However, it's also possible this one could line up on the holes left between. You can see that, while indeed the purple filled some holes in between three of the white atoms, there's still holes that can be observed between the purple that go through the white. The blue could line up on those. If it does that, you effectively have three different looking layers here. The purple was offset in two directions, the blue is offset in one direction from the white. Depending on how you stack these, you'll get different densities of atoms together, you'll get different arrangements of material. There's a lot of different ways to combine atoms into a solid structure. So how do we discuss those then? Well, in general, we don't look at the layers, we look at what's called the unit cell. Once you have a nice rigid arrangement, you can find locations where you can make a cube connecting from various atoms. And sometimes this is cutting atoms just at the corners. Depending on your packing pattern for your layers, however, it's possible that instead of just having something where you capture a corner of each atom in this cube and then could stack another to expand it in every direction, you might also have ones where you've got half of atoms on the faces. You also might have atoms trapped on the inside, and then other atoms parts around the corners and the faces. Just depending on how you put it together, where you can find a repeating unit that you could then stack multiple of together to create the overall shape will vary depending on that original stacking. Well, different forms of stacking have different densities, different amounts of atoms that tend to be inside their unit cell. And so we have several types of unit cell. There's the simple unit cell, which is just the simple cubic. This comes from when your layers are perfectly on top of each other. You just get a nice unit cell where each corner contains 1/8 of an atom, and then you can stack those infinitely. You can also get a body-centered cubic. This will have one atom trapped on the inside and 1/8 in each corner. You can also get a face-centered cubic, in which case each face of your cube will have half of an atom in it, as well as the corners will have 1/8. And there's a few other designs that can come as well, especially as you get to hexagonal structures. The idea is that the unit cell is just a way to visualize a solid. Stacking the layers on top of each other works for looking at a few, but if you want to talk about an infinite arrangement, something moles in size, you can't really draw that many atoms stacked on top of each other. And so we look for the smallest repeatable unit. Well, these result in various physical properties. How dense is your material? How strong is your material? Things like that. This unit cell can have an effect on that. This is also governed by what ions are pairing or what materials are stacking. An ionic compound needs to arrange the positive and negative ions in such ways to get them all close together in the right pattern so that you don't end up with a whole bunch of negatives in one spot and a bunch of positives in another. Depending on the relative size of your cation and anion, this can make certain unit cells more preferable than others. This can also then lead to certain shapes that we see. Crystal formations, how many sides a crystal tends to form, if it makes nice long crystals or kind of branches in all directions. A lot of that comes from the unit cell. What's the repeating pattern and what directions does it tend to go? These are things we tend to know after the fact. We have to determine them. You can't just look at a formula and know what it's going to do. So how would you go about seeing the pattern of the atoms? For this, we have Xray crystallography. Xray crystallography is an incredible technique of using trigonometry and film to calculate out how far every atom is from its neighboring atoms. When you have an arrangement of atoms and you shoot an X-ray source at it, well, as your X-rays fly into it, they tend to deflect. If you then slightly rotate this material, change its angle just a little bit and shoot again, that deflection pattern will change very slightly. So if you've got a piece of film and you see where the original pattern shows up, and then you turn just a degree for your crystal and you look at where your pattern now shows up, they'll start to move. The spots will change positions. Their relative position to one another changed in the crystal versus the X-ray beam, and so where they show up on the film will alter. Taking many, many images, rotating in many, many directions, allows us to start to see how each atom was lined up, and as we rotate the crystal, how they spread out from each other. This can be back calculated to figure out how far apart the atoms had to be and at what angles to each other. In the old days, by hand, this would take you a very, very long time. Today, with the computer, it takes you a couple hours to run the X-ray, takes you a couple hours to process the data, if you're reasonably skilled. But generally, you can get a crystal structure within 2 days in the modern world. And so that tells us what was our packing pattern. Was it AB? Was it ABC? Exactly how did this all go together? And allows us to calculate out the unit cell structure. So it's a very impressive technique that lets us explore these solid packing forms. It also lets us discover far more information, such as atomic radius. When you have, say, covalent molecules that you cool down sufficiently, like Cl2s, well, you'll get one molecule that is two chlorine atoms stuck together, and they're covalent. They overlap. But you also can have a neighboring Cl, and that isn't covalent with the first one. It doesn't overlap with the first. However, they will get right next to each other. Maybe they'll be offset, but however they line up, there's a difference here. From the nucleus of the covalent ones versus from the nucleus to the non-covalent ones, there's a difference in that distance. This actually lets us calculate out the radius of an atom. There's a covalent radius, which is effectively from the nuclei to halfway between to the other nuclei. There's also what we call a van der Waals radius, which is for the electron cloud, which says, hey, between unbonded nuclei, well, let's just go halfway. There's a radius here. What we'll find is that the van der Waal will be one length and the covalent will be shorter. Which makes sense. The covalent is about overlapping your orbitals, where the van der Waal is just, why do they not get closer? Well, that's where the edge of the electrons bump into each other. This is actually why some of our data for atomic radius occasionally can seem a little bit odd, depending on where and how they were calculated. We might be looking at slightly different terms when we're talking about radius. If you think about the radius for, say, a metal atom, is that covalent or is that van der Waal? They're sharing electrons, but they're all kind of evenly sharing in all directions. And so it can be a little bit problematic depending on what type of radius you're talking about. But this allows us to actually figure out what some of those differences are in order to figure out just how big is an atom really. Which finally leads to some of the ideas of how do those materials pack together? If you have atoms stacked together, well, there's a few ways that this can happen. You could have, say, noble gases like argon, where you just have free independent atoms stacking on top of each other, making a solid. These have very weak attractive forces. The only thing holding them together is London forces. There's no dipoles on a noble gas. There's no ions. And so our noble gases tend to be gases because there's not much holding them together. It is possible to get liquid and solid for most of the noble gases. Arguably on Earth, you cannot get solid helium. There's some tricks for it, but effectively you cannot get helium cold enough to turn solid on Earth, not helium-4 at least. However, you can think about other atomic materials like potassium. If you have potassium, well, that's just a block of metal. It's still atomic, but because it's metal, it's sharing in all directions. It actually has electrons that are shared, and these are nice and strong, and so it holds together very well. In this case, neither of these are really intermolecular attractive forces. These are individual atoms, but really intermolecular are interparticle forces. These are cases where we're looking at monoatomic particles, but really the same idea. What's holding them together? What's the strength that is holding them together? That helps us see what kind of material we expect. Noble gases don't share. We expect them to be gases. Metals do share. That's much stronger. We do expect them to be solids most of the time at room temperature. And that's what we see for most metals, mercury and gallium aside. As this then increases to small molecules, you get your dipole interactions attracting things. The more dipole interactions you can get, the stronger those are, the more likely you are to be solid. And so while water is usually liquid at room temperature, despite having two fairly good dipoles between that OH, something like sugar, so glucose, well, it has many OH bonds. As a result, it has lots more interactions that it can have, and sugar tends to be a solid. It's also a little bit heavier. However, the extra weight doesn't add nearly as much as the attractive force of more dipoles. And so by having more dipoles, more OH bonds in this case, sugar is significantly stronger at holding on to other molecules, especially more sugars, and so it tends to be a solid. And so making our molecular solids is about how strongly those molecules tend to adhere to each other. If you just had something like propane, which is significantly heavier than water, it's still a gas at room temperature. It doesn't have dipoles. Weight is not what's governing being liquid, solid, or gas. Attractive forces is. And so the more attractive forces, the stronger they are, the more likely you are to be solid at any given temp versus lesser attracted material. Which then leads to our minerals. Ionic compounds tend to be extremely likely to be solids, Well, there are some advanced materials where you can have liquid ionic materials, and we may discuss some of the advanced materials in our lecture in class. In general, normal ionic materials tend to be solids. These are salt crystals and minerals and rocks because they have extremely strong attractive forces due to the full-on positives and negatives being attracted to one another. And while solids do have a great deal of properties that emerge from those intermolecular forces, such as strength, brittleness, conductivity, and the like, they're not quite as easy to calculate and predict as it is for liquids with things like vapor pressure. Due to complicating factors in the crystal structure and arrangement of materials, as well as doping with slightly different atoms such as carbon and iron, affecting how it can play out in its large crystal structure, predicting the properties of solids tends to be a little bit more problematic. We'll talk about some of those that we've discovered and how we've overcome them more in our in-class lecture.